Hi, welcome to Lab 5, first order sensors. So for the first part, the circuit hardware, I built the circuit over here. Moving on to the MATLAB simulation code, which you see right here. You see here that the blue curve, which represents the 10K ohms, has a smaller time constant than the red curve, which is 100K ohms, because the time constant tau is equal to RC. Looking at the graph, it can be seen that for the 10K ohm resistor, charging the capacitor will be faster, and for the 100K ohm, it will be slower. That is due to the time constant. So this is my Arduino code right here. At the top, I define my variables, the pins. In void setup, I set the BPS rate to 115,200. And I define the pin modes for my VC and VN pins. And then starting, I'm setting VN to be low for 5 seconds. So this is my void loop. So it's asking us to get a reading at time intervals of tau divided by 50. And we're supposed to hold the 5 volts and 0 volts for a period of 10 tau. So that means there are 500 intervals. So we have this first while loop where it's going to go from 0 to 500. And so we set the VN high, and then we read what the actual value is, and we read what the VC drop is. We make that into a string, and then we print it to the serial monitor. And then we delay for 20 tau. Then we increase the time interval by 1. So this next loop is for when VN is held at 0 volts for 10 tau. So we set the pin low, and we read the values in, and then we make the string and print to the serial monitor. And then we delay for 20 tau again. Then we decrease the time interval by 1. So it goes from 500 back down to 0. So this is the serial monitor. You can see that works properly because on the V inside, it's going from 5 volts, which equals 1023, to 0 volts, which equals 0. And that's the VC on that side. So this is still the 10K ohm resistor, but I made a quick mistake. I defined these as ints before, but they should be floats. And this is the serial line for the 10K again. You can see it's going from 0 to 1023, so high and low. And the VC is on the right. Now I changed the 100K ohm resistor. And you can see I changed it in my code. And on here, say the trials are 0, so it's currently discharging. And discharges, and give it the input of 5 volts, so the 1023, and it charges back up the VC, so the drop is more. And this is the code for the processing part. So moving on to void draw, and this is my lines. I use the function line, and to write the text, like 0 volt, 1 volt, I use the text command, and define the size and the color. And I made a legend by defining the fill and the circle for the legend and the text size, and what the actual text is right there. And I just randomly picked these locations to make it look nice. Moving on to standard part code, which I didn't change because it was already there. Lastly, if the cursor X is off the 1200 size, it's going to refresh by doing background again. So this is the output for the 10K ohm resistor, and these are the lines and the text, and that's the legend right there. And you can see the lines are, when it's at 0, it's at 0 accurately, and at 5 volts, it's accurate. So you can see it's charging up, discharging, discharging, charging. Now this is the 100K ohm resistor. You can see now it takes a longer time to charge and discharge. That is because the time constant is greater for the 100K ohm resistor. And everything else is still the same for the legend and the lines and everything. So this is the MATLAB code for data analysis. And the only thing I changed in this code was to make the ADC codes to the voltage. So for the 10K ohm, what you do first is import your data file. The left side is the code side, and the right side is the voltage side. And you can see that it doesn't match up closely to the theoretical, because for the 10K, it should be like, the peak should be up here instead of like down there. 100K ohm resistor, I already changed the value and I imported the data file for that. And this is the graph for it. You see how the time range changed down here because of the time constant that changed. So it changed down here. And this is more accurate to the theoretical than the 10K ohm. Ohm resistor again, and I found that to make it more accurate, now you can see that's more accurate. If you change the baud rate from 115,200 back down to 9,600, you get a more accurate graph. So for the sensitivity of the output voltage to be maximum, the R needs to equal 10K ohms. So moving on to the thermistor circuit, this is my Arduino code for that. So I have the pin, and this is my circuit with the resistor. So starting with part 1, heating the thermistor. Right now you can see it's at stable room temperature because it's at 2.5 volts. And this is a thermistor and this is hot water. And I'm going to dip it in there and see how that responds on there. So one more time, if I dip it in there, it's going to decrease, and that's the time response. So step 2 is cooling the thermistor. And right now you can see it's stable. And when I put it in the ice water, you should see the response go up. So the thermistor circuit for the last question does behave as intended. So you saw as the temperature increases, the resistance of the thermistor decreases, and thus in this equation, the V out equation, the V out also decreases. On the opposite hand, if the temperature decreases, the resistance of the thermistor increases, increasing the V out. So for example, it closely follows this curve.